A sphere of radius r is inside a closed cylinder of radius r and height 2r. When r equals 8 centimeters, calculate the volume inside the cylinder which is not occupied by the sphere. The volume not occupied by the sphere would be the volume surrounding the sphere, which would equal the volume of the cylinder minus the volume of the sphere. A cylinder is just a prism, so to find the volume of the cylinder, we can do cross-sectional area multiplied by length, and the volume of the sphere, we have a formula for, which is given in the question. The cross-sectional area of the cylinder is a circle with radius r and the length is 2r. So for the volume of the cylinder, we know that it's pi r squared multiplied by 2r. The radius of the sphere in this case is also r, therefore we can just leave that as it is. And we can simplify this expression to give 2 over 3 pi r cubed. The question says that r equals 8, so to find the volume, all we need to do is substitute our r with 8. Find r when the volume inside the cylinder not occupied by the sphere is 36 centimeters cubed. From the question, we know that the volume not occupied by the sphere is equal to 36 centimeters cubed. And from part 1 of the question, we have an expression that represents that volume that is not occupied by the sphere. So that means that that expression equals 36. And now we have an equation with an r, and we can use this equation to solve for the value of r. B. The diagram shows a solid cone with radius 5 centimeters and perpendicular height 12 centimeters. The total surface area is painted at a cost of $0.015 per centimeter squared. Calculate the cost of painting the cone. The total cost of painting the cone would be equal to the total surface area multiplied by the cost per area, which we already have from the question. A cone has two faces, so the total surface area would be the area of the circle at the bottom plus the area of the curved surface. The area of a circle we all know is pi r squared, and the area of the curved surface the question gave us a formula for, which is pi r l, where l is the slant height of the cone. The radius r is given in the question as 5 centimeters, but we do not have a value for the slant height, so we need to find out the slant height first. The slant height of any cone can be found by imagining a right-angled triangle inside the cone with the radius as one side and the perpendicular height as the other side. This means that your slant height would be the hypotenuse of the right-angled triangle, and we can use Pythagoras to find out L. From Pythagoras, This means that 5 squared plus 12 squared must equal L squared, and we can use this to solve for L. And once we have the value of L, we have everything we need to calculate the cost of painting the cone. The cone is made of metal and is melted down and made into smaller solid cones with radius 1.25 centimeters and perpendicular height 3 centimeters. Calculate the number of smaller cones that can be made. Assuming that no metal was lost in the process of making the smaller cones, the number of small cones that we can make would be equal to the volume of the big cone divided by the volume of the small cone. But we do not have a formula to calculate the volume of a cone. But it's important to remember that if we did need the formula of the volume of a cone, then the question would have given it to us. This means that we do not need the formula for the volume of a cone, because we will be doing volume divided by volume, and that would cancel out the formula anyway, as you will see now. To calculate the volume of any shape, you need 3 side lengths. For example, a cuboid needs base times height times length. A cylinder needs pi times radius times length. The volume of a sphere was given to us in the first part of the question as 4 over 3 pi r cubed, and we know for a fact that the volume of a cylinder is pi r squared times L. So we can assume that the volume of a cone would equal some number multiplied by pi multiplied by height multiplied by r squared. We can let k be this number for now, and we don't have to know the value of k. So if we use this formula to calculate the volume of the cones in the question, the volume of the big cone would be k times pi times 12 times 5 squared, and the volume of the small cone would be k times pi times 3 times 1.25 squared. And as you can see, the k and the pi cancel out because we can divide the top and the bottom by k and pi, so it doesn't really matter what value k is. And therefore, the volume of the big cone divided by the volume of the smaller cone equals 64. This means that we can make 64 smaller cones from that one big cone. There's also another method you could use to do this question. Sometimes with geometry, when you've gone through all your options, don't forget that scale factors also work. In this case, if you notice that the height of the smaller cone is 3, but the big cone is 12, and the radius of the smaller cone is 1.25, if you compare the radius and the height of the small cone and the big cone, you can notice that it's multiplied by 4. Right? The height and the radius of the smaller cone multiplied by 4 equals the height and the radius of the bigger cone. This means that the scale factor is equal to 4. And this also means that the two cones are similar, so we can use scale factors to solve this question. However, don't forget that when you're working with volume, you need to cube your scale factor. This means that the scale factor for the volume would equal 4 to the power of 3. So this means that the volume of the big cone would equal 64, which is 4 to the power of 3, multiplied by the volume of the smaller cone. So when we calculate for the number of small cones we could make by doing volume of big cone divided by volume of small cone, it would equal 64.